lab, we needed to find the mass of a black hole, which we found to be about 3.161 times 10 to the 31 kilograms. While it is impossible to observe a black hole, you can observe the motion of objects around it. Given position and time data of an orbiting star as well as the mass of the star, it is possible to determine the mass of the black hole. We are required to assume that the star is only orbiting the black hole, that the black hole is not moving, and that no outside forces are acting on either the star or the black hole. In order to calculate the mass of the black hole, we first need to calculate the velocity of the star. Velocity is simply the change in position over the change in time. Given 2 points, we are able to calculate the velocity of the star between those 2 points. After that, each new point given is a new velocity. Once we have at least 2 velocities, we are able to calculate the change in momentum over the change in time, since momentum is simply the mass times the change in velocity. By rearranging Newton's second law, F net equals mass times acceleration, we are able to make it such that the change in momentum over the change in time is equal to F net. From there, we can set F net equal to the universal gravitation equation, g times m1 times m2 divided by r squared, where g is the universal gravitation constant, 6.7 times 10 to the negative 11th. With that, we can arrange it to solve for the mass of the black hole. Also with this information, we are able to determine dp dt parallel, dp dt perpendicular, f net parallel, and f net perpendicular. Since dp dt parallel is just the rate of change of the magnitude of the momentum, we can just use the equation the magnitude of the momentum final minus the magnitude of the momentum initial divided by the change in time. Since we already had both dp dt and dp dt parallel, we can just use the equation dp dt equals dp dt parallel plus dp dt perpendicular to find dp dt perpendicular. Just like with f net and dp dt, both of the equations f net parallel equals dp dt parallel and f net perpendicular equals dp dt perpendicular are true. Using these equations, we're able to use the programming language VPython to come up with an approximation of the mass of the black hole, using the positions of the star, which are given to us in this document. Then, using the code given to us, we insert the equations we calculated earlier into the code. We start with calculating the velocity and momentum. From there, we add in the equations for dp dt and f net. Then we added in the equations for dp dt parallel and f net parallel, as well as the equations for dp dt perpendicular and f net perpendicular. Finally, we add in the rearranged universal gravitation equation, which has been written in 2 lines of code for simplicity. Then we run the code, and here's the model of the star going around the black hole. The yellow arrow is f net, the blue arrow is f net perpendicular, and the black arrow is f net parallel. As you can see, the yellow arrow points directly towards the black hole. The blue arrow points either in the same direction as the momentum or in the opposite direction of it, depending on if it is speeding up or slowing down. And the black arrow always points inwards towards the center of the kissing circle, perpendicular to the momentum. Earlier, we showed that f net and its components were equal to dp dt and its components. While they are numerically equal, they are not the same thing. When we use f net, we are referring to the forces acting on the objects, and in the parallel and perpendicular cases, the forces acting in the parallel and perpendicular directions, respectively. dp dt is the change in momentum over the change in time. dp dt parallel is the change in the magnitude of the change in the momentum over the change in time. It is only non-zero when the object is speeding up or slowing down. dp dt perpendicular is the change in direction of the change in momentum over the change in time. It is only non-zero when the object is moving in a nonlinear motion. If we were to remove the current black hole and put in a new black hole in the same location with the same mass, the motion of the observed star would remain the same. It would be impossible to tell the difference because the only force acting on the star is universal gravitation. Since we are assuming the mass of the star is remaining the same, the only thing that could affect that force is the distance between the star and the black hole and the mass of the black hole, but both of those are staying the same as well, so the orbit of the star will remain exactly the same. Using the universal gravitation equation, some position data from a star, and the programming language VPython, we're able to estimate the mass of a black hole.